Hi everyone. In this video, I'll present our CVPR 2026 paper, How much 3D do video foundation models encode? This is a joint work with Xiang Li, Zhaoyang Liu, and James Ray. Let's start with the motivation. Videos are continuous 2D presentations of the 3D world, and they are far easier to collect and scale than handcrafted or scanned 3D assets. They are naturally photorealistic, diverse, and abundant, which makes them a very attractive source for learning 3D. But there is a catch. If we just chain on in the wild videos, there is no explicit signal forcing the models to learn 3D, and there is real ambiguity between ego motion and scene dynamics. So the question is, does 3D understanding emerge anyway, just from large-scale video training? This paper is the first model-agnostic study of 3D awareness in video foundation models. We studied along 4 axes. Extent: how do video foundation models compare to image models and to specialized 3D experts? Factor: what drives 3D awareness? Localization: where inside the network does 3D live? And the implication: can these features actually help downstream 3D tasks? And our approach here is pretty simple. We probe the frozen features of various video foundation models to estimate 3D properties. Specifically, we estimate 3 scene properties from the frozen video foundation model features: the global 3D points, camera poses, and per frame depth maps. If a video model encodes 3D, a small probe should be able to read this out directly, with no fine-tuning of the base model. The pipeline has 2 stages. First, the frozen video foundation model extracts spatial temporal features from the video. Then we sample 4 frames and past area features through a shallow VGT-style probe. It consists of 4 alternating attention layers and 3 readout layers for points, depth, and pose. The base model is never updated. Whatever 3D the probe recovers was already inside the features. Note there is one caveat here. What if the probe itself is doing all the 3D reasoning? To roll that out, we add a control group using the per frame dyno features. If the probe itself is doing all the 3D reasoning, then the 3D estimation from the video foundation model should be close to dyno. On the other hand, we use faster features as the upper bound reference. It's a model explicitly trained for 3D point prediction and poses. That gives us a real 3D representation to compare against. For data, we train the probe on Code3D V2, which is a data set of 10K object-centric videos. And we also have experiments on DL3DV, which consists of 6,000 large scene videos. We also created a 2,700 ablation set for sweeping experiments. The ground truth is generated with VGT given its accuracy. Our baseline span the spectrum. We have 2.1, OpenSora 2.0, and Calc Video X as the representatives of video diffusion models. There's also Ether, which is Calc Video X fine-tuned with 3D objectives. And we also include VJEPA as a self-supervised video encoder, plus our 2 controls. On Code3D, the ranking is shown on the right. There are main 2 takeaways. First, on the extent, strong video diffusion models show great 3D awareness. 2.114b is close to faster, the 3D expert. Second, all video models beat dyno V2, so temporal reasoning is doing the real work. On DL3DV, which is the in the wild scene dataset, the ranking is similar, but there's 2 new findings. On extent, 2.114b actually outperforms faster on this more out-of-the-domain challenging dataset. And on the factor side, 3D fine-tuning isn't actually a free lunch. Ether wins in domain on Code3D, but loses on DL3DV. This means specializing for 3D with limited fine-tuning data might actually hurt generalization. Our qualitative results align well with the quantitatives, where one shows clearly the best results, while Dino V2 fails in reconstructing the scene in many cases. We also tested the factor of scaling. Here we consider hot video X to B versus 5B, and 1.3B versus 14B. The results here are mixed. One improves dramatically with scale, but hot video X is slightly worse when upscaling. So the conclusion here is that scaling actually helps within a family, but the training recipe might matter more than the parameter count alone. And for the localization question, which basically is where does this 3D signal live? We basically did a grid search over the diffusion time steps and layer depth for the generative models. The pattern here is remarkably consistent across the three models we considered, where low noise time steps combined with mid-layer features gives the strongest 3D awareness. So if you want to extract 3D, that's where to tap in. Finally, all of this pays off. We trained a full VGT model on a frozen 2.114B feature instead of Dino. It actually beats the standard VGT with Dino with less than 10% of data. Note that we basically control the training data to be the same. So this is basically saying that when the 3D training data is pretty limited, video features are a strictly better foundation for training these reconstructors. To wrap up, state-of-the-art video generators are quite 3D aware, sometimes better than the native 3D models. And temporal reasoning is the key. 3D fine-tuning helps in domain, but can hurt out of domain. And video priors gives you data-efficient 3D reconstruction. Thank you so much for watching.